Hi, this is a pre-calc video, and the topic is about a polynomial function. We're specifically interested in looking at this particular line. So what I have constructed here is the tangent to the curve, and I've labeled the point of tangency B. Up here I have the x value of that point B, and I have measured the slope of the tangent. And we can see that the slope is changing as I drag the point of tangency along the curve, kind of like a roller coaster. Now, what I'm interested in doing is plotting out, given the x value of the point of tangency, I want to map out the slope of the tangent. So this will be my domain, and this will be my range, or this will be my x, and this will be my y. And what I've done here ahead of time is I've used a little interval here of x values increasing by a half. And so if you just give me a second here, I'm going to plot out these values. Here are the points, and what I'm going to do is just do a rough connect the dots here. Okay, there's my best freehand attempt. Looks like some kind of curve, although I did my best to make straight lines. You could see that could it possibly be a graph with 3 roots? Maybe a cubic? My next idea was to increase the accuracy. I changed the interval instead of going every half. So here's a graph with some more data about every 0.125, so like every eighth of a unit was my idea here. I wanted to get another data point for the slope of the tangent. So now what I've done is I've increased the number of inputs to try to get a better picture of representing all of the slopes of the tangent as we move from, in this case, from left to right along the graph. I want to map out all of these tangent values. So give me a second here, I'll plot some points. Alright, I've graphed these points as well as I could, and I'm definitely seeing some kind of pattern here, or some kind of path. I'm starting to think this might be a cubic function. Each one of these data points where I took the x value of point B, which is our point of tangency, and I took the slope of that tangent as my y value and plotted them out. So let's connect them so we can get a better picture here. Alright, this looks pretty similar to our first graph. Certainly we're getting more detail. And if you can follow the logic that if we increased the number of x values and plot out the y values, the idea behind calculus is we want to do this infinitely many times. So that any instant as point B moves along from left to right, I can stop at that instant and measure out the slope of the tangent. And I can do that an infinitely number of times, and what that will give me is the graph of a curve, which is what we're approaching here as we get more and more detailed about the points that we plot and increase the number of points. Now, a few things on this table that should be of interest to us are these little locations here where our y values go from negative to positive. Tends to make me think that there's a 0 value in there. Could there be some domain value that gives me a 0 as we're going from negative outputs to positive outputs, and then the positives get larger and then they start to decrease, and then here's another location where we're going from positive to negative. Can there be a 0? Will there be zeros at these points? Do you see where we're looking at my little makeshift graph? And then as we go further into the negatives, there's another turnaround. We're heading back to the positives, and here's another location. That's our third. So those correspond to these, and what I'm starting now to wonder about is, will there in fact be zeros? Mathematical logic tells me that there will be. And this also relates to our fundamental theorem of calculus, which we'll learn about later. Alright, let's cut to the chase. Let me get rid of this graph, hide this table, and again revisit what it is we were measuring out there. As we went from left to right, we were plotting the value of the slope of the tangent as determined by the x value of the point of tangency. So this is our independent variable, and the slope of the tangent is dependent upon the location. What we've been after. This red graph is the first derivative of this polynomial. And let me show again the parameters so that we can start to examine a pattern here. Alright, what I'm going to do is I'm going to rewrite our quartic function, which is this blue graph. I'm going to replace our a value with the value from the parameter, which is at the moment 2. These are adjustable, and in another video I'll come back and we'll look at some of the results of adjusting these parameters and watch the changes on both the graph of the quartic and of its first derivative, which is cubic. So at the moment we have 2x to the fourth. My b value is -2, so this is minus 2x cubed. My c value is -4, so this is minus 4x squared. D is 2, that's plus 2x. E is 1. My constant is 1. And you can see that the y-intercept is 1, f of x. Now the first derivative, f prime of x, is 4 times a. A is 2, so this at the moment is 8x cubed. 4 times 2 is 8. 4 minus 1 is 3. What we're doing here is learning the power rule. We're going to use this first derivative power rule when we're looking at graphs of polynomial functions. And as we work through the year, we will build our understanding of how this is accomplished, why this power rule works. My next term in the first derivative is 3 times b times x squared. B is 2, so this is really minus 6x squared. And let's look at the power rule pattern. 3 times -2 is -6. 3 minus 1 is 2. 2 times c times x. C is -4. So that's -8x. Right? That's the third term of my first derivative. And again, the power rule. 2 times -4 is -8. 2 minus 1 is 1. And now, plus d, what's d? 2. Plus 2. Now we have 1 times 2 is 2. 1 minus 1 is x to the 0. Thanks for watching. Keep practicing.